Hi everyone. So in the last video I kind of had to rush through things and I didn't get to show you an actual computation of a definite integral. So I thought maybe you could, in this video, maybe you could discuss some of the basic rules and in integral calculus and actually use the reverse parallel rule, which is the most basic way of integrating. But at the same time I kind of wanted to clarify what an antiderivative or what an indefinite integral is. So let's just begin. So if we differentiate x to the power of n, that means we're getting n times x to the power of n minus 1. And now, how do we integrate that function? Well, remember, integration is just the opposite function, the opposite operation of differentiation, not a function, sorry. And so, how would you get to that original x to the power of n? Well, we could increase x to the power of n plus 1, and then that's great because we would get rid of this. And then how do you get rid of n? Just, now after it has been differentiated, it would be decremented, so it has to be n plus 1. Okay, so then this reverse power rule, or so-called reverse power rule, nobody really refers to it as a reverse power rule. It's not like a consensus amongst mathematicians, it's just the way I call it. But that's what it says. If we start with a function like 3 to the 3x squared, okay. So if we want to differentiate that, it's going to be 6x, right? Move that to here. And then how would we integrate that? We would integrate it using this formula at first. It should be like natural instincts at some point in your integration course, but for now we're going to use the formula. And since this is the same thing as 6x to the power of 1, we increase that power by 1, we get 2. And that basically means we end up having 6x squared, but actually we're dividing by that number as well, so we end up getting 3x squared. And that's the same thing as what we started off. But there's something here which we are not quite sure on, because say if I started with a constant as well, it can be anything. Let's start with 10, okay? If we differentiate that, that's going to become 6x plus 0, right? 6x, because constants don't change the rate of change. So then, when we integrate, how do we know whether there's been a constant or not? And actually, if you see this symbol here, this c, which I kind of ignored in the beginning of the video, the constant of integration, often regarded as mathematicians as annoying, possibly unnecessary, but it is very necessary in differential equations, which I'm going to discuss in a different series. But for now, let's just kind of stick to this rule that when we integrate such expression, we would have to add a plus c, because it could be a constant which got lost in the process of differentiating. It doesn't mean that what we're integrating here is a function that got differentiated. It doesn't mean anything, but this is a consensus among mathematicians. And so also I should like to introduce to you, and by the way, what we just did here, that's the same thing as working out the indefinite or indefinite integral or antiderivative from with no bounds of 6x. That's basically what we did. And that's what an antiderivative means, or an indefinite integral means. It just means you're taking an expression and changing it, transforming it into the integral form, using a formula just like this. Now, a definite, or a more specific kind of integral, that would be from a to b of that function. So for example, a equals 1, and b equals 5, okay? And how do you work it out? Using the rules that I've possibly shown in the last video. All we need to do in which case is just we need to find the expression, we need to find the antiderivative, and we've already said about the same thing, but that's our antiderivative. But when we go to the realm of definite integrals, we can ignore the constant, because what we're assuming is that there's a function and we need to work its area rather than finding the original function which got differentiated. So you see, it's more kind of specific. It's not general. It's not for finding the reverse of a derivative and trying to kind of figure out if there was a constant before. No, it's just specifically for finding the area under the curve. And so what we do is we do 3x squared, and often you see this notation here. That just means we're iterating, we're finding, we substitute 5 here, and then we minus it from a substitution with 1. So we do this. And what is that? Well, that is 3 times 25 minus 3, or 3 times 1. If you're going to be a bit pedantic, that's 75 minus 3 equals 72. So that's our first definite integral there, which is very exciting, because I don't know, if you ask me personally, I always found it amazing, intriguing how you can use calculus to work out curves which would seem impossible to find the area of in real life, because this here is a quadratic essentially. We end up having an actual quadratic, and it's amazing. In this particular case, it's very simple because we're integrating like a line function, a linear function. But if I was actually showing you, like, I don't know, integral of this thing here, integral of 3x squared, so we could say the double integral, just like have double differential, which means the second differential, and then we would have the area under a very curvy kind of curve, so something which would definitely be impossible to work out in with our current knowledge of geometry with no calculus. So here's an example that calculus is very useful. Just quickly making sure you understand that other kind of rules in calculus which are deemed to be quite minor in integration, but rules which I definitely would say that we can't ignore. So one of them is the constant rule. It just says that if you have an integral of k times, with k being a number, a constant, times function of x, that'll be the same thing as k times that integral. That is really, really useful. Actually, that's probably the most ubiquitous kind of rule, because if you're going to be doing like logarithmic integration, yes, that exists, or trigonometric integration, you're going to be having to do this all the time. Then, needless to say, if you have an integral of, say, 3x plus 5 dx, or any other polynomial, you'll just be doing the integral of that plus the integral of that, and just keep doing, even if it's like negative. Just like you have a subtraction rule, you'd have the addition rule, just like you have them in regular differential calculus. So I'll see you in the next video, and I think what we'll be doing next is probably just solving some basic examples. Hopefully then I'll get to make some videos about U substitution and then integration by parts, and I'm gonna explain what those means. From there, I think I might make a video or two on limits, and then return to the good old real analysis, function analysis. Then I might make a bunch of videos on series calculus, although I think most of you probably don't really need it because it's pretty damn easy. And then I might make a video on integration, on the integrational equivalent to implicit differentiation, which is differential equations, and that's where things get a bit interesting. So separation by variables, slope fields, and all that kind of stuff. And that's like, I think it's equivalent to Calculus 1, like last semester, I'm not sure, but here in the UK, in A-levels, we tend to do differential equations at the end, like right at the end of the A-level maths course. So that's not really as urgent. But for now, keep awesome, keep practicing calculus, and I'll see you in the next video.